Cinderella, Cinderella, Cinderella. You my Cinderella.
First question says, how many protons and neutrons are there in the nuclei of the following isotopes? Iron, 56, 26. Iron is 26, 56. 26 protons. 56 minus 26 is going to equal 30 neutrons, and because it's and we need to know protons, neutrons. Okay, they don't ask anything about electrons. If the question asked anything about electrons, it would equal the number of electrons, the number of protons. All right. If the iron had a charge, positive, then that would be an indication of either electrons lost or electrons gained. All right. The next one was uranium. Now, uranium is uranium-235, and it has 92, the atomic number. So it will have 92 protons. Yes, and 235 minus 92 would equal the number of 143 neutrons. Once again, if they asked for the number of electrons, it would equal the number of protons because we have a neutral element. Yes, it'll, for example, if I had that, then the number of electrons will not be equal. Plus 2 means it has lost 2 electrons. Yeah, so it would be 24 electrons. Okay. And if it was negative, it would mean it had gained electrons. Then the next one is uranium-238. Still 92 protons, but the isotope is 238. So 92 protons, because it's the same element as there. And the number of neutrons is going to equal 238 minus 92. So it is equal to 14. Is it 6? Yes, 6 neutrons. All right. Any questions there? There shouldn't be problems. Right, then. The next one, using the relative atomic masses given in the table, in the periodic table, calculate the relative molecular masses of the following compounds. Now, the first one is ammonia. So, what is the relative atomic mass of nitrogen? It is 14, and hydrogen is 1. But how many hydrogens have I got? 3. All right. So I have got a total of 17. The relative atomic mass does not have units. Okay. The next one is carbon dioxide, so CO2. Well, carbon has a mass of 12, and oxygen has a mass of 16. But how many carbons are there? Well, 2 of them. So in total, I have a mass of 44. Yeah, bye. Joshua, did you do them? Okay. The next one, copper sulfate. CuSO4. The mass of copper, 64. What's copper? Yeah, 63, but we can round it off to 64. I think your tables have 64. 64. Sulfur is 32, and oxygen is 16, but how many oxygens are there? We have 4 oxygens, so the total mass, 192. And lastly, we had glucose, a sugar molecule. Oh, did you only do up till C? All right, let's do glucose, C6H12. 06. Well, it is going to be 6 times carbon is 12 plus 12 times hydrogen is 1 plus 6 times oxygen, which is 16. Did any of you work it out? That one. 180 for the relative atomic mass. All right. Okay. Now we have to carry on with the periodic table. And then just very simply, people, the structure of the periodic table. We have horizontal periods and vertical groups. Okay. In general, we refer to 8 groups. All right, we ignore those transition metals in the middle. We don't put them into a specific group. And then the periods are the first 2 elements, hydrogen and helium, lie in the first period. Then lithium, beryllium, boron, neon lie in the second period, etc. Okay? In general, the elements in the different groups are grouped together because their properties are more or less the same. Now, the first thing that we must have a look at in terms of the different elements on the periodic table, the old exercise, you did it in grade 8 for the first time, where we're going to have a look at the electron distribution. Hydrogen has 1 electron. Right over here, next element there, helium has got 2 electrons. Yeah, you've done it. Lithium has got 3 electrons. All right. Beryllium has got 4 electrons. All right. Boron has got 5 electrons. All right, and so on. What is the pattern that we get? Can you remember?
Yeah, there's those 2 shells in the periods and in the second period.
1, 2, 3, 4, 5, 6. Oh, I've only got 7. I need another one. 8. All right? Let's just quickly do underneath lithium, we get sodium. How many electrons does sodium have? 11. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What is the pattern that we get? Yes. The period number tells me how many shells there is. The group number tells me number of electrons in the outer shell. All right? So all the group 1 elements will have 1 electron. Group 2 will have 2 electrons in the outer shell. Group 3 will have 3 electrons in the outer shell. Group 4 will have 4, 5, 6, 7, and these will have either 2 or 8. We say it has a full outer shell. Remember, the first shell can only take 2 electrons. All right, so 2, 8, 8, 8, 8. Yes, we will come to the SPD notation in a moment. You must just first be with it on this. Okay. The number of shells, people, is important because the electrons, the elements, when they form bonds, it is the outer shell electrons that are involved in chemical bonds, not the inner ones. Okay? The inner shell electrons don't have enough energy. They are held close to the nucleus. The outer shell electrons are shielded from the nucleus, and it's easier for them to be lost or gained or shared. All right. So chemical bonding occurs on the outer shell electrons. The shape of the periodic table tells us how many electrons in which shell. If I go and say to you an element like, okay, let's take selenium. Selenium lies in 1, 2, 3, the 4th period, and it lies in group 6. So selenium is going to have 4 shells, and the outer shell will contain 6 electrons. Do you understand? Okay. Now the transition metals, they form on that periodic table the green group. Now they sometimes can differ, we say, in terms of oxidation states. Remember, metals, when they form ions, they tend to lose electrons. Now we find that they sometimes can lose 1 electron, sometimes they lose 2, sometimes they lose 3, and sometimes they can even lose 4. Which means, for example, if I look at something like iron, I can get the compound iron chloride, and I can get another compound iron chloride. And they are chemically different from each other for the simple reason this iron makes 3 bonds. So it has 3 bonding places. That iron makes 2 bonds, so it has 2 bonding places. In other words, if I broke up the ions, that one is iron 3+, and that one is iron 2. So how do you know if I say, I've got iron chloride? Yes. We have to, in brackets, put in a Roman numeral 1 or 2. So the name must be iron. Oh, sorry, not 1, but 3 or 2. Iron 3 chloride. Yeah, because this 3 refers to the iron. It's got 3 bonding places. So I have iron and I have chlorine. This iron has 3 bonding places. Chlorine only has 1. So I have 1 of them, but 3 of them. All right. If I get a formula, copper 2 chloride. Copper has got 2 bonding places. If I have copper 1 chloride, it's got 1 bonding place. So copper 2 chloride would look like that. And copper 1 chloride would look like that. Do you understand? All right. Okay. So the terminologies, they have more than one oxidation state. Now, oxidation state you will do when you get into grade 12. But just take note, the transition metals can sometimes have different amounts of bonding places. It depends on what it's reacting with, how much energy is available, etc., what product will be formed. Okay. Right, now, the next section, there on page 25, the heading says, Higher Studies. And seeing as you are all busy with higher studies, you all have to know what I'm doing. Now, when we worked with atoms, we have the nucleus, all right, with the protons and the neutrons, and then in shells around the nucleus, we get the electrons. Okay, Now, if I could cut it open like that, then first shell, second shell, third shell. Are you still with me? Fourth shell. Now the first shell can take 2 electrons. The second shell can take 8. Okay, and I'll just stop there for a moment. Now, electrons tend to form pairs. How does it work? Because electrons are negative, they should actually repel. But as the electrons are moving around the nucleus in an orbit, they are also spinning on their own axis. Electrons with opposite spin will attract, yes. And that's how they pair off. Electrons with the same spin repel. Alright, so we find that within these energy levels, electrons tend to form pairs. But what they're going to do is, they first put one into position. And then the next one will come in, because it's also got to do with the energy state of the electrons. So, into the first shell goes the electrons with the least energy available, and it goes into an orbit which we call an S sublevel, and we represent the electrons with half arrows. That would imply I have electrons with opposite spin.
It's like 3 electrons.
Yes. So the first energy level has a so-called S sublevel. The second energy level, the second shell, has got 2 sublevels. An S sublevel and a P sublevel. Now these sublevels, it's got to do with the shape of the path the electrons follow when they go whizzing around the nucleus. Okay? The S sublevel is just circular. Okay, so it's in a circular shell. The P sublevels, there are actually 3 of them, and they look like this. And then into the board and out of the board, X, Y, and Z planes. And in each one of those shapes, 2 electrons can go. Now you don't need to know about the orbital shape. That's not part of your syllabus. Yes, because in the second energy level, the electrons travel firstly in an S sublevel. Alright? And then we will have 3 Ps. P sublevels that die about 90 degrees to each other in 3 dimensions. Alright? So what they are going to do first is, one will go into the one will go into the other, one will go into the next. If I am representing, let's say, element, let's say fluorine. How many electrons does fluorine have? 9 electrons. So 1, 2, 3, 4, 5, 6, 7, and now they will pair off 8, 9. How many bonding places does fluorine have? 1. Yes. All right? If I had a look at something like nitrogen, nitrogen has 7 electrons. 1, 2, 3, 4, 5, 6, 7. How many bonding places does nitrogen have? 3. Do you understand? All right. Okay, so now in the third sublevel, and this is where it deviates from our model of 28888. But if you remember correctly, we would only work with the first 20 elements. Because this model of 28888 only works with the first 20 elements. Because up to here, I will now have 10, 2, 4, 6, 8, 10 electrons. Now the next one is 3 P's and 5 D's, and that would be an S. So SPD sublevel. And the D sublevel just has a different shape to what the P and the S sublevels have. You don't need to worry about the shapes. Yeah, small letters. Let's say element number 20 is calcium. So calcium is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now it jumps that one, 19, 20. Because the picture of this is, there's our first subcell. This one is superimposed over that one. And that one is superimposed over the previous one. And what it comes down to is, it requires less energy to fill an S sublevel than it does to the D. So calcium, with 20 elements, 20 electrons, has 2 electrons in its outer shell. It fits the pattern perfectly.
Okay, so if you reach P sublevel van die tweede een,
Yes.
is already P sublevel van die derde een.
The energy level, yes. After that one, you go to that one. If I went on,
Die sublevel.
gaan nou vir jou ene wys. Let's take selenium. It's got 34 electrons. 2, 4, 6, 8, 10. Are you with me? 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30.
En dan gaan jy na die volgende
31, 32, 33, 34.
Maar is dit nie, maar dit maak nie sin nie. Hoekom sal hulle nie eers die P maak voordat hulle die D van
No, it drops back to the D. It just does because it's got to do with the energies.
Okay, so juffrou.
Okay?
But then don't you need more energy to fill up the D than you need?
No. Those on the outside have more energy. Those on the inside are pulled close because they've got too little energy. All right, it works back to front. Now, it becomes even more complicated than this because then in the fourth subshell we have SPD. So here we have D sublevels and then 7, 1, 2, 3, 4, 5, 6, 7 F sublevels. Okay. Now we won't even, it doesn't matter. It's just, you just fill them up and there's a specific order, and I'll show you a pattern how to know the order because now it starts jumping. Okay. But they don't normally ask further than this. I'll show you. I'll show you now in a moment. Okay. Yes. I'll show you. All right. But do you understand about the distribution of the electrons? Okay. Now, before I go any further, when I look at the periodic table, it's actually quite spectacular. You can also divide up this periodic table into S, P, D, and F block elements. It means the S block elements have their outer shell electrons in an S sublevel. This one will have 2 electrons in the 1, 2, 3, 4, 5th shell, the S sublevel. Okay? These are S block elements. These are P block elements. Remember, we don't work with them. Okay? P block elements. They have got electrons that are unpaired in the P sublevel. So that is where their bonding will occur. Whether it's in the first, second, third, or the second, third, fourth, fifth, sixth, seventh shell, it doesn't matter, but their electrons, their outer shell electrons will lie in the P sublevel. These are D block elements. So their electrons will lie in the D shell or subshell. F. Okay, so we have S, P, D, and F block elements. Yes. Yes, that is why they are there. Okay, there's a very specific reason for the shape of that periodic table. Yeah. Yes? 10 electrons will go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's got a filled outer shell. Ja. Ja. No, they will always go. They will always go in from the bottom to the top in a specific order. Wacht, waar is jy nou? By this? There. But this P sublevel consists of 1 S and 3 Ps. So there is place for 4 pairs. Verstaan jy? In total, I have 8 electrons there. I have, in total, 2 electrons there. Yes, the first one is close to the nucleus. The next one is slightly further from the nucleus. And then the P sublevels around it. The next one is slightly further. Remember, these shells are not solid. It's a space in which the electrons move. Okay. All right. That's it.
Win free airtime with One Africa TV. Share your comments on the channel. WhatsApp your feedback, name and town to 081 200 6659. One Africa TV. It just gets better.
Okay, grade 11s. Yesterday, we had a look at the molecular shape, all right, of the different molecules, linear, angular, pyramidal, and tetrahedral, and we had a look at the repulsion between electron pairs, lone pairs, and bonding pairs, bonding, lone pair, all right. And we explained the shape of the molecules. Now, we are still busy with bonding in general. I did mention water, that is a polar molecule. If you look in your textbooks on page 31, they discuss the different structures and the angle on the left-hand column in the block at the top. On the right-hand side, they discuss the water molecule. It has 2 lone pairs. So the structure of water is similar as it is shown in the table. The structure explains why water was attracted to the charged ruler. We said water is a polar molecule. I said to you yesterday, why is water polar? Because if we look at the bond of oxygen and hydrogen, that's the hydrogen, oxygen, oxygen, we have the electron pair repulsion, pushing down the hydrogens at an angle on the one side of the molecule. Yes. But if you go and look at why is oxygen the slight negative side and why is hydrogen the slight positive side, then it has to do with the oxygen molecule has got two lone pairs of electrons. They are negative. So